my name's Will. I work on the Neo4j developer relations team. And today I'm going to be talking a little bit about graph data science with Neo4j Graph Algorithms. So here's the agenda for what we're going to talk about in the next 30 minutes or so. First, we'll talk a little bit about what is graph data science, what are graph algorithms in that context. We'll talk a bit about the Neo4j Graph Data Science Library, which is this library of these algorithms that let us run this in Neo4j. And then hopefully, if we have enough time, we'll spend a fair bit of the session hands-on looking at using this graph data science library in Neo4j browser. We'll look at how we can use the results of these algorithms in graph visualization with Neo4j Bloom, sort of as a way to interpret the results of these algorithms that we run. And then we'll take a look at a no-code approach to graph data science with the graph algorithms playground in Neo4j desktop. And then we'll talk a little bit about some resources for getting started. Cool, so let's jump into it. So we're talking about graph data science. So let's back up a step and understand what we're talking about when we talk about data science. So this image is inspired by the data science Venn diagram that Drew Conway, I think, first created, gosh, probably at least 10 or 15 years ago. And his point that he was trying to get across is that data science is really this interdisciplinary field that combines things like, he called it hacking, but basically being able to write code, combining that with math and statistics, and then with a healthy amount of domain knowledge for sort of whatever problems you're trying to solve. And all of these things together, the intersection of these three things together is what data science is all about. And ultimately, we're talking about answering questions using data. So then when we're talking about graph data science, this is now a subset of data science. So we're answering questions with data, but specifically we're looking at connected data. So this is when we're using the relationships in our data in addition to just sort of discrete data points to answer questions. That's fundamentally what graph data science is all about. And just like data science in general, it's multidisciplinary and multifunctional as well, right? So we use different tools together. We use graph algorithms, queries, graph visualization. We use all of these things together to be able to answer questions with relationships in our data. So if you're familiar with graph databases and Neo4j, you may realize that there's really this spectrum between what we think of as local graph queries or local traversals and global graph algorithms. So when we're writing a Cypher query that is saying, find this pattern where it exists in the graph, maybe I'm looking for a movie recommendation. So I'm going to start from a user node and traverse out to the movies that they've rated. From those movies, traverse out to other users that have rated those same movies, and then traverse out to find what other movies those users who have rated the same movies as me have also rated higher. So this standard sort of collaborative filtering recommendation query. If I'm doing that kind of query, that is on the local end of the spectrum, where I have a well-defined starting point. I'm taking advantage of index-free adjacency to traverse out from there. And that's the kind of thing that the graph databases are optimized for, that they're really, really fast and able to do these traversals. Now, on the other end of that spectrum, you have graph algorithms that don't have a well-defined starting point that they traverse out from. These are often iterative global operations that are touching every piece of the graph. These are things like running PageRank on the entire graph, or community detection, these sorts of things. And of course, we can use these together. Oftentimes, the results of our graph algorithms then feed into to local graph queries. So in our recommendation example, oftentimes it's useful to calculate PageRank or personalized PageRank in the context of a user's network to be able to provide them with recommendations influenced by the more influential nodes in their network. So this is a spectrum and things we can use together, but in this talk, we're going to be focusing more on the graph algorithms end of the spectrum. So we're going to be using the Neo4j Graph Data Science library today. You may have previously seen what was called the Neo4j Graph Algorithms library. And the Graph Data Science library is really the next iteration of that library. So the Graph Algorithms library enabled running these global graph operations on Neo4j, and the Graph Data Science library takes that concept and sort of makes it enterprise grade, more stable, more optimized. So think of GDS, as we call it, the Graph Data Science library, really as the next iteration of the Graph Algorithms library. There's a very similar concept, slightly different syntax, and under the hood, optimized performance, essentially. Cool, so in this graph data science evolution, I guess is one way to think of this. If we look back at when we were talking about the spectrum between local and global, we can think of knowledge graph queries as more on the local end of this, right? So going back to our movie recommendations, if we have a graph of movies and the actors and the genres and things like that, this is the kind of sort of decision support knowledge graph type query that we can use. Now, then when we move to graph analytics, we're talking about looking at statistics about the network, looking at counting the degree of every node, running graph algorithms like PageRank, community detection, those sorts of things. And beyond that, we have things like graph feature engineering, where we're using graph algorithms to uncover some feature that then maybe feeds into a machine learning algorithm for classification, maybe an unsupervised algorithm, something like that. And then forward looking beyond that, we have things like graph embeddings, where we have some way to encode or represent a graph that can, again, feed into another algorithm. You have things like deep neural nets and so on. But what we're going to be talking about today is this graph analytics piece, where we're talking about using graph algorithms with graph data science. Cool, so there's basically 5 types of algorithms that are available to us in the Graph Data Science library. And there are pathfinding and search, centrality or the importance, community detection, link prediction, and similarity. So pathfinding allows us to find, for example, the shortest path between 2 points. We may want to take weights into account, right? So these are things like A* for routing, or breadth first search, these sorts of things. Next category is centrality. And these are algorithms that allow us to find the most important or the most influential nodes in the network. So things like PageRank, betweenness, centrality. The next group of algorithms is community detection. And here we're interested in finding clusters or partitions in the graph. So a way to sort of group similar entities. Maybe they're users who interact together frequently. Maybe they're movies that end up belonging to the same genre, this sort of thing. The next group of algorithms is link prediction, where we're looking for, trying to identify if there's a sort of hidden link between nodes that may not be represented explicitly in the graph. And then the final category is similarity. And similarity is interesting because this is not really, I should say, most of these algorithms are not really graph algorithms. They're often based on set comparisons. So things like Jacquard similarity or cosine similarity, where we're comparing two sets, but they're really, really useful in the context of a graph. So here, for example, we may have run, let's say, like a natural language process on a bunch of documents and extracted the entities mentioned in these documents and represented that in a graph. And then we want to calculate the similarity between these document nodes. And we can do that by comparing the overlapping entities mentioned in the documents. This would be a way that we could use Jacquard similarity, for example. Or things like cosine similarity, where we're comparing maybe the ratings of movies for users in a user-rated movie graph, something like this. So those are the general categories. Here's a glance at the different algorithms that are available in the Graph Data Science library for these different categories. I think there are maybe 45 or so of these. And you'll see some of these are in bold, and these are the ones that are the most optimized and that are sort of at the product level tier of support. The others may be more experimental or not performance optimized implementations. But they're still available to us nonetheless. Cool, so how do we actually use these algorithms with the Graph Data Science library? So the Graph Data Science library gives us procedures that we can then call within Cypher, and we'll see hands-on how to use this in a minute, but I just want to sort of show the syntax for these procedure calls. So the basic syntax is we use the call keyword. This indicates we're calling some procedure, and we say call GDS, so GDS for Graph Data Science, that's the namespace for these. Then we have an optional tier. So I said earlier that we have some algorithms that are the product tier, so these are the most performance optimized. These are going to be in the product tier namespace. Then we reference the algorithm that we want to run. So this might be like GDS.PageRank. Then we have the execution mode. So there are three basic execution modes. We can run the algorithm and then stream the results back without sort of updating the data in the database. We can, and that's the stream execution mode. We can run the algorithms in the write execution mode, where we're running the algorithm and then writing the data back to the database either as a node property, or some of the algorithms such as the similarity algorithms will create a relationship between nodes. But either way, in that mode, we're updating the graph. And then we can also run this in stats mode, which will give us some statistics about the results of the algorithm, such as how long it took to run, the min and the max, this sort of thing. And then we can also just estimate the memory requirements for the algorithm. So if we don't actually want to run the algorithm, instead we just want to make sure that our machine is configured appropriately and we have enough resources to performantly run a specific algorithm with a specific configuration, we can add on this optional estimate procedure at the end. Now, what are we passing in to this procedure call? Well, we're passing in a graph name. So these procedures allow us basically to construct an in-memory graph that we're actually using to run these algorithms. So we can either name the graph, which can be sort of a subgraph or a projection that we can define with Cypher. So the graph that we're running the algorithm on doesn't actually have to exist in the database. So this is a really useful feature of the GDS library that we'll see an example of in a minute. So basically, we build up this in-memory graph, and then we pass along some configuration. And the configuration here depends on the algorithm, whether we want the weighted version of label propagation, for example, or specifying source nodes for PageRank, something like that. So it depends on the algorithm that we're running what the configuration is going to be. Okay, so here are the different tiers. So we have the product supported tier, and in that case, we just leave the tier off. Those are just in the GDS namespace. Then we have the beta tier. These are algorithms that are, think of them as, I guess, sort of candidates that will be moved into the product supported tier eventually. And then we have the alpha tier, which are the more experimental, less optimized algorithm implementations. So use these ones sort of at your own risk. Cool, so how can you make use of this? Well, first of all, if you're using Neo4j Desktop, the graph data science algorithm is available in the plugins within Neo4j Desktop. So you can just click add plugin for a database and you'll see it available. Note that you cannot use both the graph data science library and the Neo4j Graph Algorithms library together. They're not compatible, so be sure only to install one version of those. You can also use graph data science with the graph app that's called the Graph Algorithms Playground within Neo4j Desktop. We'll take a look at this in a minute. And then you can also make use of the results of some of these algorithms using Bloom, which we'll also take a look at in a minute. And Bloom is also now included in Neo4j Desktop by default, so you shouldn't need to do anything to install Bloom now. If you have the latest version of Desktop, you can just start it as a graph app. And then if you're not using Desktop, you can download the Graph Data Science library directly from neo4j.com/download center. There's also a link here to the documentation. Cool, so what I want to do now is let's jump over to Neo4j Sandbox. So Neo4j Sandbox that Lou showed us earlier, this allows us to spin up some Neo4j instance that's hosted for us in the cloud with some preloaded data, and also includes the Graph Data Science library, so we can run these algorithms. So I had just started this Graph Data Science project. So if you click on new project, you'll see lots of these different ones available. This specifically is Graph Data Science, and I just clicked on open with browser, and it brings me here in Neo4j browser. So the Graph Data Science sandbox, this includes a data set that's been extracted from the George R.R. Martin Game of Thrones series. Basically, it is looking at character interactions where we have two names that appear within 15 words of each other, then we consider those an interaction. There's also some more data. It actually combines a few different data sets. Let's look at called DB schema visualization. And this is a bit difficult to look at first because we have lots of multiple labels here. So let's remove king, knight, and dead from our schema visualization. Basically, those are multiple labels that are added to person in this case. So we have things like the battles that different characters were in, the house they belong to, which book they appear in, things like their status. I think this is, are they still alive or dead at various points in the books. But then we also have these person to person interaction relationships. And you can see we have interacts 1, interacts 2, interacts. And the reason for that is we have different measures of interactions throughout the different books. But basically that's what we're going to be looking at, are these person interacts with person pieces of the graph. So the first thing that I want to do is create one of these in-memory graphs. And to do this, I say call GDS create graph. We give it a name, GOT interactions, and then we give it all of the nodes we want to consider. So in this case, the person nodes, and then we give it the relationships we want to include in this in-memory graph. And I want the interacts relationships following both directions. So I'll run this, and this will load. Now we have this GOT interactions graph that we can refer to later on when we're actually running our algorithms. And the first algorithm that I want to run is PageRank. So we'll say call gds.pagerank, and this is going to be the streaming variant of it. We pass in the graph, the GOT interactions that we constructed previously. Then this call is going to yield a node ID and a score. So to get back the properties from the actual node, so in this case, we want to know the name of this person, we can use this GDS util as node function, passing in the node ID. So this bit here is going to give us the actual node that we just ran PageRank on, and we're grabbing the name property and the score. So this is the PageRank value, and ordering the results by the score. This should give us the top 10 characters by PageRank. We have Jon Snow, Tyrion Lannister, Cersei. So if we're familiar with the books, this sort of makes sense. It's also interesting to compare PageRank to other sorts of centrality measures. So here we're running PageRank, we're getting back the nodes. Then here we're calculating degree and weighted degree. So degree, this is just the number of interacts relationships that each character has. And then weighted degree is summing up the weight. So for each character, for all of their interacts relationships, we have a weight property, which for any given pair of users, this weight is the number of the interactions between those two users throughout all of the books. Now, if we add that up, then we get a metric called the weighted degree centrality. So here, if we're comparing, and we've ordered by PageRank here. So Jon Snow has the highest PageRank score, but note that he does not have the highest degree centrality or even the highest weighted degree centrality. So PageRank is giving us a bit different information because it's this sort of recursive algorithm. We're not just simply looking at degree and weighted degree, which may not necessarily find the most influential node, depending on how we're defining that. Cool. So far we haven't updated the graph. We've just streamed the results back. We can now write the PageRank values back to the graph using GDS PageRank write, and we specify the write property. So this means that we'll calculate PageRank, and then we will add a property value on the nodes called PageRank. So if we want to now find all of the person nodes, we can just p.name and p.pagerank, right? So now we can see person's name, their PageRank score is stored in the graph. Let's run one more algorithm, and then we'll take a look at how to interpret these results in a visualization. Let's take a look at a community detection algorithm. In this case, we'll use label propagation, which can take into account weights. So we need to create a weighted in-memory graph. The previous one we created did not specify any properties to include, so that was an unweighted graph. So now we're going to create a new in-memory graph called GOT interactions weighted. We want this looking at the person nodes, following the interacts relationships, undirected, but now including the weight property. So if we run that, we now have this GOT interactions weighted graph that we can then pass into our label propagation algorithm, specifying we want to consider weights for this algorithm, and then write a property back called community. So this algorithm will assign partitions, communities to each node and write that as a property. So we can do something like this, match all the persons, get the community property as community, and we can group by community, gives the count of the persons as the number in the community. And now look at the community and its number of nodes assigned to it. Let's just look at the top 50 of these. Not sure how many we actually generated. Okay, and we can see here the sort of distribution of the size of the number of person nodes assigned to each community. So we have community 304 has almost 400 person nodes, then the next is 100 and sort of so on. So we have really just a handful of large or medium-sized communities. Okay, so we've run our algorithms. We can see how we can kind of query some of these results using Cypher. But let's take a look now at Neo4j Bloom to see how we can visualize some of the results of these algorithms. So Sandbox includes Neo4j Bloom. So first I'm just going to copy my password and then we'll open up Bloom here. So Bloom allows us to explore Neo4j graphs visually. And first thing we'll do is sign in. So the user is Neo4j, and that's the password I copied from Sandbox. So Bloom allows us to sort of explore the graph without having to write Cypher. And it's configured by what's called a perspective. So perspective can define the type of data that we want to visualize. It can give us some styling for different pieces of data. So we loaded that perspective. That's going to give us some styling for our graph. So the first thing we can do is let's just search for person nodes. I'm just going to zoom out a little bit here and see a bit more. Cool. So the first thing we notice is that we have 1,000 person nodes that have been rendered here, and they're different sizes. So let's click on one of the bigger ones here, and we can see this node represents Tyrion Lannister. We can see his PageRank score. We can see which community he's been assigned to, but he has one of the higher PageRank scores, and he's showing up as larger in the visualization, which is great because we can look at this and very quickly identify the most important nodes in the network. And in Bloom, we have what's called range-based styling. So if we look at the configuration in the perspective for person nodes, we see that we have this range-based style rule that says size nodes relative to the value of the PageRank score. So where the value is higher, make the nodes bigger so that I can quickly see the more important nodes in the network, which is great. And we also notice though that these are different colors. So if we go back to our person rule-based styles, we can see that we have a rule that is setting the color based on the community value. So for all of the nodes that are in the same community, they're being assigned the same color. So we can quickly look at the graph to sort of make sense of which nodes belong to the same community. Let's clear the scene here. And now I'm going to run this top characters and connections search phrase. So Bloom allows us to define what are called search phrases, which are essentially parameterized Cypher queries that we've defined within the perspective. I had a typo in there. There we go. Top characters and connections. So this is running a Cypher query that we've defined in the perspective, which basically says find the top person nodes by PageRank and then find what characters they've interacted with. And if we zoom in on this, we can see that not only are the nodes styled by size and color with the results of PageRank and label propagation, but we can see we also have relationships that are thicker than others. And this is because now if we go to the relationships, let's just select the ones we're showing in the scene, in the perspective configuration, we have a rule-based style for relationships that says basically style them related to the weight property. So if the weight property is large, make those relationships thicker, which we can sort of verify. Let's select this node. So this is Rob Stark. If we look at his relationships, and let's just filter for only the interacts relationships, we can see, there we go, that we have different weights assigned to these different interactions, and that here Rob Stark and Theon Greyjoy has a much higher weight, so we're seeing a thicker relationship there. So just useful to sort of look at the graph at a glance and being able to interpret some of the results of these algorithms. So we have a few minutes left. There's one more thing that I want to look at, and that is in Neo4j Desktop. Here I have the same data set loaded in Neo4j Desktop, and I've installed the Graph Data Science Playground graph app. So let's start that up. The Graph Data Science Playground, or you may also have heard this referred to as NEuler, this allows us to run graph algorithms using the Graph Data Science library, but without writing any Cypher statements. Instead, we have this nice sort of query builder. So here we want to run, let's say, betweenness centrality on person nodes following the interacts relationship. Let's write it back to the graph. We can run this and we get the results. So here's the betweenness centrality scores. Number one is Jon Snow, followed by Eddard Stark. But we also can look at chart visualizations, so very quickly see the results here. And we can also look at graph visualizations. So here we're looking at a section of the graph where we've styled the graph according to some of the algorithms that we've run. So in this case, the node size is styled according to betweenness centrality. So this is really useful if we're not sure the configuration option for different algorithms, if we're not sure sort of which algorithms we want to run. This can be really useful for just sort of building up experimentally some of the procedure calls for the algorithms with their different configurations. If we look in the code tab, we can see what Cypher queries we're actually building up with the configuration for these different algorithms. And we can even generate a Neo4j browser guide. This is useful if we're sort of working with a coworker and we want to send them just a quick link that has embedded in it all of the the configuration for a certain algorithm that we've created. Cool, so that is the graph data science playground. I just want to end on a couple of slides pointing out some resources here. So the first thing I want to mention is how you install the Graph Algorithms playground. So if you go to install.graphapp.io, you can see lots of different graph apps that are available to add into Neo4j Desktop. Here is the Graph Algorithms playground. We just click this install link, and that will deep link into Neo4j Desktop to install that. Here's a list of some other resources, and I'll drop a link to the slides in the chat here, and we'll share the slides so you have the links to all of these. But the download center that we talked about, the Graph Data Science Sandbox is on here. The sort of authoritative resource for all of this is the O'Reilly Graph Algorithms book, which you can download for free. So be sure to check that out.